We discussed about what are the problems with and how the memory is managed, what problems are there, how we can do that. Then we talk about that memory. There are two types of memories we are saying, or address spaces. One is logical address space, and other is physical address space. So this should be very clear in your mind. Both are different. Is there any doubt about these two? Why these are different and how these are different? Let me know, because this is the core concept of virtual memory, and this is very important. Now, logical address space is how you as a programmer developed it, and how your CPU would see it. That is logical address space. So the CPU would create, uh, basically we talk about PCB. So PCB has some location. So it is logically, it is contiguous to M space. So it is logically contiguous, and it is as it appears to your CPU, but it is being mapped physical address space. Now physical address space is your RAM. So here is your RAM. So it is physically mapped to the logical address here, or it is called virtual address. The logical address or the virtual address is mapped to the physical address, and actually the data is then taken from the RAM or the physical memory back to the CPU. So is there any confusion about logical address spacing and physical address spacing, or can I move forward? Okay, thank you so much. And in today's lecture, we are going to talk about virtual memory and how it is managed, why our program or programmer can think independent of the size of the RAM, what functionality is given and provided by operating system. That's what we are going to talk. Now, this was the main concept, that we want to take many processes simultaneously in the RAM, so as to have a better multi-programming. So an operating system functionality is to take as many program as into RAM, so that active, so that we can say that it has higher multi-programming. It provides us more multi-programming environment. So we, as of now, we discussed about the entire process must be in the memory before it can execute. So we talked about that the program, the binary files are loaded into the RAM, and then they are mapped to an address space, and CPU start uh, calling the instructions and the data set from RAM, and starts executing the process. Now, in this, we assumed that the whole of the program or the process is kept into RAM, because we want our operating system to be multi-program, so we try to keep as many processes as it could be. Now, if we say we need entire process into the memory, it is going to take a large amount of memory from RAM. So that decreases the multi-programming. Now, what we are going to discuss is we are going to divide each and every we have already discussed about pages, we have already discussed about frames. So let us suppose there are 20 frames related to one program. So this statement says I have to keep all these 20 programs into RAM, but virtual memory concept says we need not to keep all these 20 into the RAM, but we can, let us suppose, let's take just 10 frames. So whatever is needed for a program to be executed, only those would be called, because now we have divided that into frame. We will be calling the frames which are needed, and we will not be calling the frames which are not needed. So the virtual memory technique that allow the execution of processes that are not completely inside memory. So this is the core concept. What is virtual memory? One of the major advantage of this scheme is that the programs can be larger than the physical memory. So here the developer, uh, you know, got some relax or relief, he or she need not to look at what is the RAM of the computer. So they can independently develop the program, and it is the task of operating system or the virtual memory to manage the program efficiently. So it also this technique frees the programmer from the concern of memory storage. Virtual memory allow the processes to share file. Now this is another thing that we are going to discuss. Now, what are the benefits and why it is possible? We know that there are error code, so there are exception handlings, unusual routines, those are not needed. Large data structure is there. So we have declared, let us suppose, an array of this much size. We don't need that memory as of now. So we have some routines, those are not fully or completely required. Let us suppose we are asking some user to do some task based on the options. I want the user to select the options, and uh, based on those options, the program would respond. Now, if I say I have to put everything into my RAM, then I have to take the data, the process fully from the secondary storage, put into the RAM. But that would take a lot of memory, which would be unused. Let us suppose the user only want option one, the other out of 10 options would be unused, and their memory consumption would be unused. So what we want is we just want the frames those are needed by the program or the process to be taken into RAM, and that would save us memory, and we can increase the multi-programming because we are not fetching all the frames for all the processes, but only those are required. So entire code is not needed at same time. This is also another thing. So there are the routines, error codes, unusual routines, large data structure. We don't need that. So we need not to put it. Entire program code is also not required. Now, so what would be the benefit if we are able to run our program based on the features that we have basically just the required piece? We can say that the program no longer constrained by the limits of the physical memory. Each program takes less memory while running, and this increases the CPU utilization and throughput with no increase in the response time and turnaround time. So throughput is the number of like how fast your program is executing, and then less IO is needed. So there are few benefits that comes with when we are doing implementing or executing programs using virtual memory. So to repeat, this whole is a concept that rather than bringing whole of the code and the data into the RAM, we just bring in those frames for each process those are needed, and that would increase the level of multi-programming because it will leave enough RAM for more processes. It would also increase the throughput. It will also increase the less IO is needed because we have smaller size of the program that is to be shifted, and it makes our program independent of the physical memory. So we have virtual memory concept. So the only part that is needed is taken into memory, allow address spaces to be shared. This we have already discussed in the previous lecture also, how they are sharing, because the pages, we can say that a page and the frame, those can be mapped. So logical address space is different and the physical address space is different. So we can have the same frame could be called into different process or number of pages. That would allow us to share the processes, allow more efficient process creation. This we are going to discuss, and allow less IO is needed. So here we can see that these are the number of pages. Now pages are represented in the virtual address space. This is our virtual memory or the logical address space or virtual address space. So this is our virtual address space. Now from the virtual address space, memory mapping unit, MMU, would map the information from, from the virtual address space to the physical address space, and the physical address space is being fed by the backing store. So here is your hard disk or your NVM or your NVM, so flash memory. So this could be anything, the backing store, then you have RAM, then you have memory management unit, and here is a virtual memory. So this is basically is in PCB. So PCB is representing the information which is needed for a process. It includes your logical addresses which your program would be accessing. So this we have already discussed how it would be done. So just a recap, virtual address space is a logical view how the process is stored inside memory. So your brain should actually map it and visualize that there are two address spaces. One is how the CPU seeing or how the developer sees it, and the other is how it is actually stored onto the physical memory. Onto the logical address space, we have created pages. A program or the process is divided into pages. And onto physical address space, it is divided into frame size. So frame size is equals to page size, and your memory management unit is doing the mapping. Now we discussed about invalid and valid bit. That would do the magic of which page is to be kept into the memory, physical memory or not. So meanwhile, the physical is so logic MMU is doing the mapping. The virtual memory concept can be implemented by demand paging or demand segmentation. So we are not going to discuss this. We are going to discuss demand paging only. So this is your virtual address space. So we remember this is PCB. We discussed in the starting chapters. So we have code, data, heap, and stack. So they are increasing. As they are increasing means we have to allocate the physical address to actual addresses as they are increasing. So if they increase, we have to allocate more frames to this particular process. And now we can share some space. We can share the pages. Like this is the PCB for process 1, and this is PCB for process 2. So we can share some pages here. So this is shared library, this is shared library, and this could be actually stored onto frame number, let us suppose 4, 1 to 4. So this is how both of these processes would keep the page number. Their page number would be 1 to 4. Their page number could be 10 to 14, and but they are mapping into frame number 1 to 4 by memory management unit. So I hope this is clear to you, because this is the basis of what we are going to discuss today. Now moving towards demand paging. What is demand paging? So as name says, we demand the pages and it is presented on request. So demand of pages is there. So based on the demand, the pages are presented to the CPU and bring into the main the physical memory. So demand paging concept is just to bring those pages into the main memory or into the frames those are needed or asked. So rather than one way is that everything is bring into the main memory, and other thing is just to bring the pages those are needed. Those would help us to have less IO, less memory needed, faster response, and more number of users or user processes those can run. So this will increase the multi-programming level. So how this is done, we can see we discussed about swap in and swap out. So what is swap in? Swap in is bringing the page from the secondary storage into physical memory. Swap out is the process of putting back the frame back to the secondary storage. So we are going to discuss about swapping with paging. So today we are going to discuss that. So page is needed based on a reference bit. So remember in the previous uh, lecture we discussed about the page table, which each entry would have one bit, valid or invalid. So what are valid? Those are required, and those are available in the physical memory and required by the CPU. Those are invalid here. We are going to give a new definition to this, what is invalid. So the basic concepts here are uh, with swapping pages, guesses what pages will be used for swapping out again. Instead, page brings in only those pages into the memory, those are needed. And now we have pages, those are called memory residents, and those are called non-residents. Let us suppose whole of your program is into the RAM, then all the pages are called resident. So the process is resident, and in that case, there is no difference from non-demand paging. So what is non-demand paging here is that everything that is needed is already into our RAM, and we do not require any demand for requiring more pages. So that is non-demand paging. Every page is already into it, then there is a no request for new page, and those are called memory residents. Uh, so how this magic is being run is using this valid invalid bit. You remember in the page table we discussed about these things. So valid is the frame which is allowed and logical in a logical address space. So that particular frame, now frame here is the index. So here are the index 0, 1, 2, 3. So these are page numbers 1, 2, 3, 4, so on. So it means that, let us put this is I is invalid, this is I. So page 0 is invalid, page 1 is valid, page 2 is valid, and page 3 is valid. Here we will be having the addresses. So frame addresses would be referring to the memory address. So this is very clear. This is what we have discussed. Now, what is the meaning, the new meaning of invalid here? So valid, we know that it is in memory and memory resident. A frame, a page, page 1, V is set. So valid invalid bit is set for it. So it is valid here. It means that the address is in a logical address space and frame is inside the memory. I means, now I has given two meanings. One is either it is not in the address space. The second meaning is it means that the address is not into the main memory. Clear? So this is the difference given. So for simplification for today's lecture, you consider that I means that the page is not in the main memory, but is needed by the program. V means the page is inside the main memory. I hope this is clear now. Any questions till now?
Could you re-explain what a memory resident program is?
Pardon?
Could you please re-explain what a memory resident program is?
Oh, memory resident program. Oh, so
Yes.
this one, memory resident. So memory resident means that this is our physical memory. Now these are all frames. I talk about page number 1. So page number 1 is at, this is 1, 2, 3, so on, 3, 4, 5, 6, 7, 8. Let us suppose this is 8. So page number 1 is located at 8. So this is this thing. So V means that the page is in the physical memory. Let us suppose we say I. This is I here. So this means the page is not inside the physical memory. So the pages with valid invalid bit V equal to V or set is called resident, memory resident. So the frame is actually residing. This page 1 is actually residing onto the physical memory. If I is invalid, it means that the page is not inside the physical memory and it becomes non-memory resident. Is it clear?
Yes, that makes sense.
Okay. So memory resident means you will get a frame inside physical memory. Memory non-resident means it is not yet bring into the main memory. So this would be valid, but not into the main memory. So for simplification, we are just considering right now, for example, I means the frame, the page 0. This means that the page 0 is not into the physical memory yet. So what we need to do is we need to bring it into some location and then make this as v. So we are going to discuss about that too. So the concept of valid and invalid bit is used to distinguish between the frames those are actually available onto the physical memory, and v is for which is available memory resident, I is which is non-resident. Okay, the similar thing is happening here. So let us suppose we have these pages. So page number 0 is located at page number 4. So now the page number 1 is invalid here. We can say it is invalid. So it is not available inside the memory. We can see this. Now page number 2 is available at location 6. So we can go there. So these are memory residents. And similarly, page number 5 is also available and inside the main memory. So these are 3 frames are available out of 8 pages. So here are 8 pages and here are only 3 frames. So we discussed about in the previous lecture that whatever is the number of page, that similar frames would be needed. But we haven't discussed that we need to bring in all pages or the frames or all information into the main memory. So this is our logical address space and this is our physical address space. So what I did is, rather than bringing all pages into respective frames, we bring in only 3 pages which were needed or asked by the CPU. So whatever I'm demanding, only that is being fetched from the secondary memory, not anything else. So this page table is able to distinguish between what is available or what is not. So how this, let us pose a situation when your CPU start running something from page B. Now you should be able to visualize what does it mean. Whenever I say CPU accesses page B, means this is an address space and it tries to fetch some instructions from there, from that particular logical addressing. So here is, let us suppose this is an address here. So here is 000. So it tries to access something which is written from here. But this is a logical address space. Do not confuse. So it is trying to access. This is how your program is. Okay, you have written the instruction. So let us suppose you have written int is equal to I. Okay, and then you do I is equal to I plus 1. Okay, so now the CPU tries to fetch this instruction. Now this is an instruction which is written and it should be from the physical memory. It has to be taken from the physical memory. So this is logical thing. This has to be changed. Now if the CPU accesses the B, which is invalid here, now what would happen, that we are going to discuss next. And when the situation is like the CPU tries to access a bit of page with the bit is I, then it is called page fault. Is this till now is clear? What is page fault? So whenever there is, whenever its CPU tries to access page number 1 and it finds that bit is invalid for it, and that becomes page fault. Is it clear? Okay. So what is page fault? Page fault is also a kind of interrupt. Okay, let me show you what would happen. This would be making more sense. Let us suppose there is an instruction load M, which was written into page B. So page B was here. So CPU is trying to access load M, and it tries to page B, goes to the memory page table for memory mapping so that it can bring it from the secondary storage or from the RAM. I hope this is clear. So load M, the CPU would request this. The operating system would then access this particular location, find that the hardware bit, the invalid or valid bit here is I. So it gives a trap. Now trap is an interrupt. Whenever there is a trap, what would happen is the process would stop, CPU would stop its functioning, perform the context switching, and generates a suitable trap to fetch the information from the secondary storage. So it will give a trap to operating system. Operating system would identify what type of interrupt it is, and then it goes to the I means that it is not inside the RAM memory or physical memory. So it goes to the backing store, bringing that block. So this is a block. So bring in the block and then look at the free frames inside the physical memory and put the data into there, and then reset the page entry for this, and the new entry for this would become valid. Now the new entry would become here, would be valid. Is this clear, or should I repeat? Anyone who has any doubt, please try to understand this, try to visualize it. Your brain should actually visualize what we are doing, but that would actually be helpful to understand the next concepts. So I repeat again. Okay, so let us take the example. Let us take the example of this. Your CPU started accessing a page here. There are some instructions in your code, and this is onto PCB, is loaded into memory, and then it is into logical address space. So basically CPU sees your logical address space. CPU would make a request for an instruction written in A. A would be started fetching. We go to the page table. We see that there is an entry for frame number 0, which is located at frame number 4 in the main memory because V is valid. Is it clear? Is this clear? Makes sense? Now, let us suppose your program is continue to execute, and then CPU make a request to page number 1, which is holding some set of, okay? So it makes an attempt to read the instruction load M, which is in page number 1, because we have divided our page process into pages. So this will go to the memory. This will hit here, the page table, because there are same number of pages here, because this is private to each and every process. So page 1 would have an entry, but for this, the bit here is invalid. Now when it is invalid, it will generate a trap. Trap would fetch the information from the secondary storage, and let us suppose B is here, and tries to put it into some location. Let us suppose 13. Once this is done, the entry here would be updated. Here is 13, and then your I would become valid V. This is a process, and this whole process, when happens, we call page fault occurred. So whenever a page fault is there, it means that your frame or the page was not into the main memory. It has to be fetched from the secondary memory and bring it back to the main memory, and then update the page table. Is it clear now? Okay, any doubt for anyone? Let's take another example. So let us suppose your CPU accesses this. So 6G, it will try to reach here. Here again, this is I. So again, now a page fault occurs. So the process is same. Trap, bring in, look in the frame, bring it back to the memory, to the free. Let us suppose this is G, and then update this. So here it is, let us suppose 15, and we say now V is this. This is new updated page table. Okay, so page table is a data structure which keeps on updating, and this is how we distinguish between the pages. Those are inside memory and those are not inside. So what is an effect? The only problem is we have all the pages inside the main memory, then we need not to generate this trap, need not to bring it again and then update the page table if we have everything inside the main memory already. But if we don't have everything, every page inside main memory, what we need to do is we need to generate a trap every time and then bring the information into the free frames and then update the page table. This is an extra burden, but this is good. What is an advantage of this is that we can keep our memory free. If our memory RAM is free, we can run more programs, number one, because in every program, there are some routines, those are not needed or those do not execute, just like exception handling. So exception handling would be executing only when the exception occurred. Otherwise, it would never execute. So keeping that code inside the memory would just be wastage of memory. So rather than keeping it there into it, we keep it onto the secondary storage. Whenever it is required, it would be called into RAM, and then the CPU would start executing once it is updated into the page table. I hope it should be clear to you like how this is managed and why this creates and frees up memory and why this helps in multi-programming. Okay, so now coming back here. So this is the same thing. The only disadvantage of page fault is that whenever the page is not in the main memory, we have to bring it from the secondary. Otherwise, there are all benefits of it. Number one benefit, RAM is free. Number two benefit, the size of the program is not constrained by the physical memory size, because we are just keeping the frame those are needed without putting and bringing everything into the main memory. So that is the only thing. And how this magic is being run, this is based on this invalid. Now let us suppose when your program starts. So whenever your program is starting, PCB is already there. It requires the instruction. So we provided the logical address space to the CPU. The CPU, what it will do, it will try to fetch in the instructions. So instructions and along with the data. So when we talk about instruction and along with the data, for the first instruction, it may be that there is no frame inside the physical memory, and that becomes a pure demand paging, because everything we have to bring it into the main memory. So what hardware support is required for the paging is, number one, paging, and other one is for swapping. So page table, we need to take care for valid, invalid bit. This is managed by our hardware. Then we have secondary memory, and the secondary memory is required. So we say swap memory. So all of you, are you aware about the swap memory? So you set up for your Linux swap memory. Anyone who is aware about swap memory? Okay, it's not important, but the only thing is this is a special kind of memory which we can create onto our computer while we are installing Linux. That would actually give us a space to be used as RAM when RAM is. So Linux system, we define swap memory also, which is usually double the size of the RAM. So we can keep that, and that would increase the performance. And that swap memory is actually used while for this kind of paging and demand paging is being used on Linux. So this is how it is being used. Now, let me elaborate this. Let us suppose our program is doing some instruction add A, B. Let us suppose this is an instruction. Now, if this is an instruction, what is the process? Computer or CPU would fetch this instruction, which is written at some address. Okay, so this is fetched, and then it starts fetching it and then decode it. So once it decodes it, it means that it came to know that this instruction would require 2 operands, and this instruction would be performing a sum operation. So when this is decoded, it will fetch the first operand. So it will fetch operand A, then it will fetch operand B, put it into register R1, put it into register R2, and then perform ALU. So R1 plus R2 is performed into R3, and then it will store this into here. We are storing R3 goes to C. So this is the process for it. Now what happens? Like, let us suppose, because the whole information is, we have split the whole information into pages. So let us suppose where you want to store C is on a page, let us suppose, which is not inside the memory. Let us suppose I want to fetch C location, which is inside this particular page and which is not available inside memory. So what would happen? So we need to perform the context switching. Context switching would be performed, trap would be generated, the frame block would be read from the secondary memory, free frame would be looked into, loaded, and then the page table would be updated. And once the page table is updated, your process would start execution again once it is being allocated to CPU. The only problem is that in this case, this whole of the instruction would start again because this was never completed and it was performed. So in the worst case, all this has to be redone, and because from start of instruction decode, because this is where the trap happened inside the instruction decoding and doing operations. So that is the worst case thing that we have to perform. Okay, now free frame list is maintained by your operating system. So here is head, then a linked list shape is done. So here are the frame numbers. So all frame numbers are kept onto a linked list, and whenever there is a trap, so a frame would be captured from the free frame is captured from this frame list, and your data is put into that particular frame, and then the page table is updated. Okay, is it clear? Like whatever we have discussed till now is clear? Any question you have? I'm just going deep into it, and I'm going to repeat it again so that you can connect all dots together. So what happens? So whenever a page fault occurs, what are the sequences? Number one, trap the operating system. So your CPU would generate some request. Operating system would look into the page table. If the valid and invalid bit is I, then a trap is generated to operating system. Is this clear till now? How we reach to first? Okay, thank you. Then once the trap is there, this is an interrupt. So save the registers and the process. So we know the context switching is being performed. Okay. So now once the context, because this is a trap, context switching is done, determine the interrupt was a page fault. So from the routine, we look into the interrupt vector table, and from there we find, okay, this is our interrupt regarding the page fault. And if it is for page fault, then the subroutine would run. What it will do, it will check whether the page reference was legal. Legal means it is allowed, number one, because we have two meanings for R. One, the address space is not legal, and number two, the page reference is allowed. So if it is legal, it is allowed. If it is not legal, then the subroutine would run. What it will do, it will check whether the page reference was legal. Legal means it is allowed, number one, because we have two meanings for R. One, the address space is not legal, is that the frame is not inside the memory. So it will check for whether it is the page reference was legal and then determine the location of page in secondary storage. Once this is done, it will issue a read from the storage to the free frame to a free frame. So it will wait in the queue until read request is serviced. So now we are here at hard disk HDD. So wait in the queue until the read request is serviced. Wait for the device seek and latency time. Begin the transfer of page to the free frame. So identify the free frame, take out information from the secondary storage, put onto the free frame. While waiting, allocate CPU core to some other process. So this is what we have done already. Receive an interrupt from the storage that the process which was started, this trap, the subroutine is complete. Now save the register and process state for other processes. Let us suppose this is a high priority process. What it will do the context switching for other processes which we started executing while waiting. Determine the interrupt was from the secondary storage. Correct the page table and other page table to show the desired page inside memory, and wait for the CPU core to be allocated to process again. Restore register, process space, page table, and then resume the interrupted instruction. So there are so many processes, those are happening. For simplistic case, what we need to consider is this. So this is the main diagram that should be in your brain is page fault. So there are many things those are happening. For understanding the concept, this diagram is sufficient. Like the process CPU request for an instruction goes to the page table. If the entry is V, it means that it is already there. Map it and bring it from here to CPU. If the entry is I, then starts a trap. Operating system will judge for what is the meaning of I here, then identify if it is request for the page, goes to the storage, read from the storage, bring it the missing page, put it into the free frame. Once free frame is done, update the page table, and then start this instruction again. So this is all. This is very kind of complex, but this gives a power to have a multi-programmed and operating system. This concept is very, very important, and that's why I'm repeating it again and again. So I hope not 100%, you are up to 50% that you got the idea what is page fault. Agree on it? Anyone who has not started even understanding what is page fault? Is there anyone? Thank you. So demand paging is, rather than bringing all the pages for the process into the main memory, we just only the limited pages into the main memory, and we then trap the system. The page fault would occur if we want a new page, and that page would be bring it into the secondary memory. So the only drawback of page fault is that sometimes the page is not there inside the main memory. We have to bring in as requested. So there are some advantages, there are some disadvantages, but advantages are more than disadvantages. And that's why page fault or demand paging is a much used concept for operating systems. So each and every operating system uses it. Now the performance of demand paging. Let us suppose if all of the frames are already inside the main memory, then let us suppose there is some memory access time 10 milliseconds. So what we would have done is just reading directly from the main memory, and then there is no latency in that case. So if P is a page fault, so we are trying to find out the performance of the demand paging. If P is a page fault, if P is 0, means there is no page fault. So in that case, there is no overhead of page fault. So if the P is 1, then every reference is at page fault. So the memory access would be more. So what would be the effective access time here? So 1 minus P into memory access time. So let us suppose here 10 millisecond is the memory access time. Here it is RAM. Okay. So 1 minus P into memory access time plus page fault overhead plus page swap out plus page swap in. So this would be the new estimated effective time which would be there if a page fault occurs. Now we try to find out that size. Let us suppose the memory access time is 200 nanosecond here. So 200 nanosecond is there. Average page fault service is 8 milliseconds. So this 8 milliseconds include trap, reading from secondary storage, finding free frame, updating page table, and so this is the average page fault service time. So this includes everything. So I just summed it up. So whenever a page fault occurs, it's gonna take 8 milliseconds. This can worse or can be better. So let's take we take an average case here. So it takes 8 milliseconds for a page fault. So otherwise the memory access time would be 200 nanosecond. If the page fault occurs, it is going to add 8 milliseconds. So what would be the estimated time if P is the probability of page fault occurring? 1 minus P into 200 plus P into 8 milliseconds. So this will be the new estimated time. Okay, so this will be the new estimated time. So we can put the value of P, then we can find out what is an estimated access time. So if we say one access out of 1000 page, so P is what? 001. So here the P is 0.001. So one access out of 100 causes a page fault. Okay, so what would be the effective estimate time? Can you put in the value of this? Do you get this? Can you match it? So 0.001 here, 0.001 into 79980 plus 200. So remember, this is in nanoseconds, and this we have converted into nanoseconds. So convert it from the nanosecond. Do you get the estimated access time? 8.2 microsecond now. Is it matching? Is it correct or no? So this is, rather than with 0.001 probability of page fault, our memory access time has increased from 200 milliseconds to 8.2 microseconds. So this is a slowdown by a factor of 40. So if this is the probability of happening a page fault, this is a slowdown by, go ahead, Shah. Yeah, you can ask. Yeah. This does not mean that it is initially, it happens that the access time would be large as we are bringing pages into the memory and only those pages are needed, then it would be very effective at a cost of multi-programming, because now our program is independent of the size of the physical memory. We could keep a large program size into our memory. Number two, our processes can share the libraries. That is also possible because of demand paging. So the benefits are more than this particular thing. So this would happen when we have kind of pure demand paging. So there's no page inside the memory, then the estimated time would be large. As we keep as we bringing the pages into the memory, then the memory access time would be much smaller. So here we are finding the effective access time, which is kind of large with this only. So if I want my performance degradation to be less than 10%, I want that it should be less than 10%. So I can find out now what I want is that the number of one page fault should occur only 4 million memory accesses. So this is how I can reduce the size of the number of page faults by increasing the size of the RAM. If I have large size of RAM, then it means that the page faults would be less because I can keep more programs frames into the main memory. This we would be discussing as we are moving forward. So how this would happen. So, but there is a penalty for page fault. This does not come free. Okay, but as the advantages of page fault are more, demand paging are more than keeping the whole program into RAM. That's why operating system chose this particular concept of bringing the data or the instructions into the main memory. I hope I made it clear. Any yes or no? Okay. The copy on write now, as we are discussing here, so we discussed about fork. So what is fork? Fork creates child, it's children, and a parent process create a child process. And whenever we say fork, we say they share the address space. This we have already discussed in the previous lectures, that whenever a fork is creating a child process, they share the address space. So some child processes run exec system call. When they run exec system call, they bring in their own data set and information, so they create their own address space. So till the time they are not creating anything, the child process is not creating any new value or modify, they can share the pages. Now demand paging or virtual memory concept allows us to share the pages. Is that right? Am I right or not? The virtual memory allows to share the share the pages between two processes. Now, if the fork is happening, let us suppose this runs a fork and creates a process 2. What they will do, they will start sharing their address space. Because of this, now this is a PCB for your process 2, this is PCB for process 1. Because their logical address spaces is different, but they are sharing the same physical address space. I hope this is clear now better. So with this, page A is shared between process 1 and 2, page B is shared between this and this, page C is shared between this and this. Now what would happen if any one of this writes into it? The other would be actually, visible it. So what is copy on write? So copy on write. Copy on write says whenever either of the process modify any page, then a copy of that page would be created into the physical memory. So that is called copy on write. So whenever some page, let us suppose the process 1 writes and modifies something into page C, what it will do, it will create its own frame inside the memory, and it gets a copy of this. So the whatever is inside now is visible to process 1 only, but not to process. So this is copy on write. And we have, so fork allows copy on write. Now if we don't want our processes or the parent process to create multiple copies, then we have a variant of fork is called vfork. So in this case, the parent process is suspended. The child process uses the address space. Vfork does not use copy on write. Remember this, it does not use copy on write. If the child process changes anything, it is done in the same space at the same location. It does not create copy on write, whereas the fork creates copy on write. So any process, parent or thread, whenever modifies the shared space, they would create a copy of that particular page. The altered pages will be visible to the parent in case of vfork, and therefore vfork must be used with caution And this is intended to be used when child process called exec immediately after the creation. Whatever the child is doing, it would be visible and done in the same address space. So that is what is where it is used. So vfork is used where we want that it should not create a copy of it rather than creates its own. And this is the difference between it. Now we have discussed about the demand paging. So now we can say let's keep only one frame for per process in RAM in main memory. Then it means that rest of the memory we can bring in, n number of more processes. So it means that we can increase multi-programming to the size of the RAM. So whatever is the size of RAM, if it is, let us suppose 1 KB for me, so I can keep 1024 processes. It means that I can increase my multi-programming level to this, but this is not true because we need, this is over allocation. If I allocate over allocation, what would happen? There are from 0 to these many processes executing, and then each process whenever execute would generate a trap for the next frame, and there would be endless traps for each and every frame. Those would, each and every process, those would be happening, and that becomes a bottleneck. So in that case, we have to set right some size of the frames which could be allocated to one process from the main memory. So that we need to fix. And if we fix it, what would happen? Let us suppose we have 40 frames. Then we could run 8 processes. Let us suppose we have 10 pages for each processes. So process 1 has 10 process pages, process 2 has 10 pages, and so on. But we have only 10 frames, 40 frames. So if we are doing no demand paging, how many processes can execute? Can somebody answer? If each process would require 10 pages and I'm not doing any demand paging, how many processes would reside inside RAM? If my RAM can hold 40 frames and I have processes each with 10 pages, how many processes can I hold inside RAM? It would be 4, because process 1 would be allocated 10 pages and then 10 frames. Let us suppose what I do is 0 to 9 is given to process P1. So I'm talking about frames here now. So then 10 to 19, I'm giving P2 and blah, blah, blah. So I can take only P1, P2, P3, and P4. Okay. So now rather than keeping 10 pages, I want to perform some demand paging. So in that, I consider that to increase our degree of multi-programming by just twice, I want to keep 8 processes inside my main memory. So what that will give me, that I can allocate each processes 5. So if I give 5 frame to each, then I can keep the 8 processes rather than 4 processes. That would increase my multi-programming by double. Is this clear? Okay, thank you. So if we can increase our multi-programming by over allocation. So if I want to keep now, I want to keep all frames. I want to keep 40 processes. So what I do, each process would be given one frame. Then my multi-programming would become 40 times. Okay, so that is basically, that is not desirable all the time. So it is possible, however, that each of these processes for a particular data may require suddenly all the pages. Let us suppose we give them 50%. Now rather than keeping 4, we just keep 8 processes Each process is given 5 frames. Let us suppose at one instance, one process required 10 pages simultaneously. How that happens? That it may be possible that there is one instruction which required data and it is spread over, different all 10 pages. So in that case, the demand paging would be problematic. And what would be done in that case? If your memory is already allocated, fully allocated to the processes, and then there is a request by additional process because there is no free frame, how that would happen would be managed by page replacement algorithm. So we need a page replacement algorithm for it. So what I mean to say is, let us suppose there is a process P1 running and there is a process P2 running. Both processes are sharing the physical memory. Each would have its own page table. Now, the CPU tries to access a page 1. It goes here. It sees that I is invalid. Then the trap is issued. The frame is read from the memory. But when the frame is read, it will see that there is no frame available onto the physical memory. Now, if this is a case, how this would handle? Now, as this process is already waiting for it, then otherwise, if we are not able to allocate this frame to this particular process, this process would terminate. And what would be done? We say we need a page replacement. So I have to change and replace and vacate one frame from the main memory to put this new frame. So that is done by page replacement algorithm. Why this has happened? Because we wanted to keep as many programs or as many processes as into the main memory to increase multi-programming. So all the frames which are available in RAM are utilized. So when they are utilized, and if there is a need of an extra frame which is not available inside physical memory, we need an algorithm that would replace the existing frame from the RAM and freeze it and put this new frame into it. So I hope I'm clear on why we need page replacement. So one process is that we could terminate the process, and other is we can do the page replacement. So now let's talk about page replacement. Let's talk about page replacement. Okay, so what we need to do is, so whenever a page replacement has to be done, we want to free one frame. So the page replacement is free the frame for replacement. So when we say free the frame from replacement, it means that we need to identify a victim, and that victim, whenever we identify, we run an algorithm to identify the victim, and once we reach that victim, we swap that victim out and then swap in the desired page at the location. Is it clear? Is this clear? Page replacement basic thing, or should I repeat?
So just to make things clear, I just want to double check if that's okay. So what it does is it swaps out one of the pages back into memory. So essentially it moves one frame from physical memory, or at least one frame or one page residing in physical memory, and then it swaps a new page in and updates the page frame table.
Exactly.
Okay.
So because inside the physical memory, we are keeping the free frame list. Now, as we are increasing the multi-programming means that we are increasing the number of processes those are kept active, and it is going to consume all the free frames. Now, because we are just bringing the required pages from the memory, it may be possible that my program requests a page which is not currently into the main memory. And what happened at same time, your physical memory is all full. Then you need a replacement space, because all all the frames, whatever frames are here, not, so this process is currently executing. Now CPU is allocated to this process for which the trap is generated. Okay, now all these can be victim, all these frames can be victim, but we have to choose the most suitable victim so that we can replace that with the new desired page. And when we talk about replacement, we say we move that to the secondary storage. It does not mean that we are that this is cleared. This means that we are moving that back to the secondary storage by swap out. This is the process of swap in and swap out. Swap out is used to put back to the main memory. So a page goes in, page goes out, a page comes in into that free memory. This is called page replacement algorithm, and that's what we are going to discuss. Now, if there is no free frame, as we have increased the multi-programming, we try to fill in our RAM. There could be the case that there is no free space. Then what would happen? Either the process which is running is terminated, or we go for page replacement. So what can be done? We can free a frame by writing its content to swap space and changing the page table to indicate that the page is no longer available in the main memory. So whatever, let us suppose this victim is there, we put that onto the swap space, and then we update its page table to show that this page is no longer inside the main memory. So remember the valid invalid bit. So that would be updated whenever we are performing swap out. So for the page for which we are performing swap in, we update its own page table. So that's how that would be happening. And then the simplistic thing is we can use the free frame to hold the page. We modify the page fault routine to include the page replacement. Now remember this thing, what would happen? I'm repeating it again. So what would happen? There is an instruction which is not there, trap is issued, secondary storage read. Now here, there is no free frame. Now if there is no free frame, we have to run an algorithm called page replacement. So page replacement what it will do, it will free some frame. So let us suppose this is a new free frame. So once this frame is available, now this is a process now. How this performed the free the space is basically put in the previous frame here. Let us suppose some information was there. Let us suppose B is written here. So B is written here. So we swap this out, and then once this is swapped out, its page table is updated, and then this particular page is bring in. Now this is a free frame. So once that is happening, this will update its page table. This page table once done would actually again set to restart the instruction, and then it is again starting that process. So this is how that is happening. So what we are going to discuss next is the page replacement algorithm. This would help us to replace a occupied frame, and there are some algorithms that we will be using. I think it is better if I discuss it in the next lecture because the time is already done. So just to recap today, I reiterated many times today. Sorry for all those who understood it. And today's concept was all about the virtual memory. So we know that logical address space and physical address space is different. Mapping is performed by using page table. So inside page table, we have a valid invalid bit that is used to distinguish between what frame is actually available on the main memory and what frame is not available onto the main memory. So whenever a CPU requests for some instruction, page table is checked. For that page, the valid invalid bit is I, trap is generated. That trap initiates a read from the secondary storage and put into the main memory. So that process would include a process of page replacement. If there is no free frame available, then an algorithm would run, which is called page replacement algorithm, that would free one frame out of the main memory to put this newly fetched swapped in frame, and then it updates the entry of the page table, and our CPU would start its instruction as and when it is allocated, and then this whole process would again start happening. Now there is disadvantage that page fault requires traps to be initiated. The advantages are that we can keep multi-programming more programs into it. The developer need not to think about the size of the memory. Virtually it becomes infinity for the programmer, because there is no limit now onto the RAM, how much program it has to be fetched into the main memory. So programmer become more relieved in designing their programs, and those functionalities actually helped the the programmer and operating system to take advantage of page fault. So certainly there are disadvantages, there are advantages for page faulting, but all the modern operating system use page fault because it also allows you to share the secondary memory. Thank you so much. And we have left with